Well, welcome back, guys. All right. Excuse me. Let's make sure. I was having some technical problems here. I'm assuming everybody can hear me okay?
Yep.
Okay.
Yes.
All right. Sounds good. So, all right. If you don't mind muting yourself, because sometimes there's a lot of feedback for other students. So if you have a question, feel free to unmute and ask the question. Okay. All right. So I sent an email telling you the day that the exam will be open. So it'll be open for 24 hours this coming Saturday. If that day doesn't work for you for whatever reason, shoot me an email to Canvas and I'll see if I can adjust the times a little bit. I'm kind of limited to when I can show that. So I believe I got every part that I needed to grade. So I have not been alerted that there's more for me to grade manually. Okay, so let us begin with chapter 5. Now here we're going to be talking about the structure, the atomic structure. Now up to this point where we were previous chapter, we finally had an idea of what the atom was, how it was put together, but not 100%, okay? We got from J.J. Thomson and from Chadwick and Rutherford that the atom's model had a nucleus where the proton and the neutron existed, and then the electrons were someplace around the nucleus. So this chapter gives us an insight as to how the electrons are placed around an atom, okay? Now during this time period, again in 1900, like I said earlier, this is where a lot of information came about, a lot of theory, a lot of experimentation to kind of build the model of the atom as we currently think it is. So, but before we can get into it, we did talk about how small the electron is. It's extremely small relative to the proton and the neutron. And we find out that the electron, being so small, actually acts like light. It has properties of light. So what we're going to do is kind of touch a little bit about light, not a lot, just to give you an indication here how these electrons behave as they travel through space. Okay, so this model here shows you this curve where you got a trough and a crest, okay? Now, if we take any point, let's say on the hill, mark that spot, and then measure the same spot on another hill or another crest, that distance is an actual measurement. And we give it a special name with that symbol that we call lambda. That is the wavelength of light, okay? The wavelength of light. Now we picked the crest, but you can pick any spot on that hill as long as you pick the same spot on the next hill. And that distance will be the same. Now, lambda is designated as the wavelength, okay? And that is the distance between peaks of adjacent waves. Now, the frequency is defined as the number of these wave cycles that proceed per given time unit, which is normally 1 second. Now, I'm sure a lot of you are familiar with that because your electronic device uses frequency. Some of you have computers that operate at, say, 2 gigahertz. Okay, gigahertz is the frequency, or 1 gigahertz. And that is how many things happen within one time period, in this case, 1 second. So if we look and compare two different wavelengths, denoted here by this diagram, we can see the distance in the top diagram from one crest to the other. That's the given distance. which we call wavelength. But if we look at the bottom diagram, the distance between one crest and the other, let's say from right here to right there, you can see that distance is much smaller than the example on top, okay? So the bottom diagram depicts something with a smaller wavelength compared to the one on top. Now, if we were to depict a time of 1 second, and we can denote that by the lines given here, okay, and here. And let's just assume that distance is 1 second. You can see that the top diagram, there's look like one wavelength per second. Whereas the bottom one, you have 1, 2, 3, about 4 wavelengths that occurred in that one same time interval, 1 second. And so the bottom one has a higher frequency. The top one would have a lower frequency, okay? So the general guideline with respect to wavelength and frequency and energy is this. As the wavelength gets smaller, denoted by that down arrow next to wavelength, the frequency goes up and the energy goes up, okay? You're familiar with a lot of wavelengths. We call it electromagnetic radiation. That encompasses all the wavelengths. On one end of the spectrum, you have radio wavelengths, which are pretty big wavelengths. Okay, we use that obviously for radio, AM, FM. Okay, on the other end of the spectrum, we have X-rays. X-rays are very small, but they're very high in energy. So much so that X-rays can go through your body. Hence, we use X-rays to look at your body, looking for broken bones and so forth, okay? So as wavelength decreases, the frequency per given time unit goes up and the energy goes up. So if we look at this diagram and you're asking you, okay, which has the higher energy? Well, looking at the wavelengths, you can see that the shorter wavelength would have the higher energy, okay? And the lower frequency would be the top one. Oops, got one more student. The top one. So B would have the higher energy, the shorter wavelength, and the higher frequency. The converse, the opposite would be true for wavelength A. Now, the electromagnetic spectrum is denoted by this diagram, where on the far right is where I mentioned before are the radio waves. These are the radio waves that exist, you know, throughout all around us. We're constantly being bombarded by all this electromagnetic radiation. Radio wavelengths are very large as far as wavelengths are concerned. They could be up in the meters length. Very, very large, and easily they don't carry that much energy and easily blocked. You know, you get in a building someplace and you can't pick up your radio station because it's being blocked. On the other end of the spectrum, you have X-rays, and even stronger than that are gamma rays. You find a lot of that all around us. We're being bombarded by gamma rays, very short wavelengths and very high in energy. What we see is a very small part. What we can actually see with our eyes, we have special cells in our eyes called cones. Cones are receptive to visible wavelength. Now, that diagram's kind of deceptive here, but that little amount that we see is very small relative to the whole picture of the spectrum. Ultraviolet, you're all familiar with ultraviolets. You get out in the sun, you get a little burn. You know, sunburn because of ultraviolets, and then a little bit less energy are the infrared wavelengths. Okay, so be familiar with this spectrum as far as the position of where the gamma rays are and where the radio waves are in visible light. Okay, now, previous chapter we were talking, we were in the 1900s, what it continues. In the 1900s, a scientist known by his name is Max Planck, very famous scientist. There's a Planck Institute in Europe named after him. He proposed a very controversial idea at the time. He proposed that energy was emitted in small bundles, and those little bundles are called quanta. Now, he
Doctor,
also, yes,
I'm sorry. I have a
you
question.
had a question?
Are the dates and the names of these people going to be significant?
Yeah, it can be, yes, as far as at least the names and what they were responsible for would be significant. As the general guideline, if something's on either written on the board, which obviously we don't have a board here, but normally when things are written or presented, they probably come up someplace. Does that answer your question? Okay, I assume it did. I didn't hear the response. All right, so we thought at this time that energy was continuously emitted, but it turns out based on Max Planck's proposal that it really is, okay, that it is a specific amount of energy that is being emitted. And each individual unit or photon or amount of light energy is called a photon. Use that in sci-fi life, photon torpedoes, okay? Now, light can be very, very powerful, very strong, very, there's a lot of laser beams can be, a laser can be strong enough to cut metal. So there's a lot of energy in light or in electromagnetic radiation. And so Max Planck proposed that energy are quantized, that they exist in specific levels or amounts of energy, and they're not continuous, which is kind of denoted here in this diagram. The far left, you see how the ball's rolling down. The incline is all one continuous, but it's really more like stair steps, okay, denoted by the diagram on the right, where that distance from the bottom ground floor is ground zero, or what we call the ground state. And then to move up to another state is X amount of energy, very specific amount of energy, okay? Now, with Planck's idea, then Niels Bohr, another scientist, again, 1913, okay, we're still in the 1900s, he proposed, and given this time period, Einstein's around here too. So we got Bohr, Einstein, Planck, Rutherford, J.J. Thomson, a lot of very smart people doing a lot of interesting work. He proposed that because of electrons being so tiny and having wave-like properties, that electrons around the nucleus occupy very distinct energy levels, okay? Very distinct energy levels, and therefore electrons, like light, are quantized. Now, the electrons orbit around the nucleus kind of like the planets orbiting around the sun, but in three-dimensional. We have to think three-dimensional here because that's what nature is. A lot of times we show models up here two-dimensionally, but we got to think three-dimensionally how these molecules are put together. Now, these orbits are called energy levels or shells. You may see it written as shells. The periodic table has 7 energy levels. Let me pull up the periodic table here real quick. If you look at the periodic table we have, and we start from hydrogen, and we go all the way down, okay, we see 7 horizontal lines. We call those periods. When we get to the periodic table, we'll give you more specifically. But there are 7 energy levels, okay? There are 7 levels, I should say, which represent 7 energy levels. In fact, like I did mention before, I will refer to the periodic table quite a bit because it's going to help you when we discuss what we call electron configuration to kind of describe how the electrons are put together around the nucleus. So 7 energy levels, otherwise called as periods on the periodic table. Okay. Every orbit has a specific radius and energy. and hence having a radius as the distance away from the nucleus. Okay, we can denote this by this particular diagram where we have the nucleus in the center, and these dotted lines represent this different energy levels. Here we only denote 3, but there are 7, okay? 7 energy levels. Not all of them are occupied. What are occupied depends on the periodic table on which element we're looking at. Obviously, the more electrons you have, which is denoted by the atomic number, for example, atom number 2 would have less electrons than element, I should say, element number 100. Number 2 wouldn't have 2 electrons and therefore wouldn't occupy all the energy levels, only the initial ones. Whereas number 100 would occupy a lot more energy levels because that's where the electrons have to come into play. Now, how do we know this? Okay. Well, it's been demonstrated that elements, when they are subjected to energy, emit light. And analysis of the light, we actually break it up with respect to their wavelengths, okay? Much like the rainbow is broken up by the water droplets up when it rains, light can be broken up into a specific wavelength, so we can analyze that, okay? So we'll have more on that in a second. Now, why did Bohr think that? Because he looked at gases that were sealed in a glass tube and then hit it with energy, in this case, electricity. It's no more than a neon light, basically what it is, but different elements inside the tube, okay? And when we plug these in, these tubes with whatever element you're looking at, it gives off light. Okay, and from the light, we can analyze it. We break it up into their specific wavelengths, and we have what's called an emission line spectrum. Now, how does that work? Okay, so this diagram here shows the tube on the far left with whatever element's in there. In this case, this is hydrogen. It's going to emit light. Okay. Now the light is run through some slits, and all that does is localize the light. And then we run it through a prism. A prism then breaks up the light into their specific wavelengths. And guess what? If you look at the bottom here and bottom right, that is the spectrum of hydrogen, okay? And that is very specific for hydrogen. That is how we can analyze from far away, analyzing the light, we can determine what elements are in there because we break them up into the specific wavelengths. And then look in our database and mix and match and figure out what's what. So that is the fingerprint for hydrogen. And each light there, each line has a specific wavelength, and each line represents a specific energy level, okay? Now, if we look at this diagram here, which shows elements like lithium, sodium, potassium, rubidium, cesium, mercury, and neon, they all have their own spectrum, fingerprint. That's how we can identify who's what. Hold on, I'm getting notified here. All right. So what is happening here? Why are we getting this? Well, a long time ago, I said nature is lazy. It doesn't like to be in what we call an excited state. If it is kicked up to an excited state, it's not going to hang out there very long. It's going to drop back down to the ground state. That's a stable state. And when it does, based on the law of conservation of energy, whatever energy I put into the system, it's going to come out, either as heat or light. So in this diagram, it shows you what happens to, in this case, this could be hydrogen. We got hydrogen with a nucleus, one electron on the first orbit, denoted by the red dot. Well, we hit it with energy, in this case, electricity. It excites hydrogen, okay? The electrons get excited. If there's enough energy, it actually kicks it up to the next energy level, okay? And that is the excited state. because that is not where it normally exists. So it stays up there for a little bit and then comes back down. And when it does that, it must emit the energy that it gained. It's going to, a lot of times it will emit it pure light, sometimes it's light and heat, but all that energy in whatever form is emitted. And that's what that squiggly little arrow represents, is the light that is given off. It's happening now if you have fluorescent light, any light, LED or the old incandescent light or fluorescent lights. You know, these molecules, the atoms in that light are being excited with the electricity. They go up to the excited state. They hang out there for a little bit and they drop back down. And when they drop back down, they release that energy as light. Hence, we have a light bulb. You see, if you have an electrical stove, you turn electricity on, your burner gets red, okay? That energy, it is electricity passing through the coil excites the molecules. Well, they're gonna release that energy that they have, and they release, in that case, releases heat, okay? All right, so that's what's happening. Now, so we have 7 energy levels, which are denoted on the periodic table by 7 shells, okay? Starting with hydrogen, there's 7 periods, horizontal lines going across the periodic table. We then find out that within the energy levels, there are what are called orbits, and there's 4 types. There's the S, the P, the D, and the F orbit, okay? So S, P, D, and F. Currently, if we find some more, then obviously they're gonna probably go with the G nomenclature, but right now we're up to F. All right, so in the first energy level, okay, there's only 1 orbit. We call that the S. And that encompasses the first period on the periodic table, which is hydrogen and helium. Now the S can handle, we'll talk about that in a second, how many each one can handle. The second energy level, which it starts off, if you have your periodic table in front of you, starts with lithium and goes all the way across the periodic table to neon, has 2 orbits. They have an S and the P. Now the number in front here of the letters represent the energy level, okay? So we have 2S, meaning it's in the second energy level, and they have the 2P, which again is in the second energy level. Notice that the first energy level does not have a P, only the S. The second energy level has 2 orbits, the S and the P. Now when we get to the third energy level, which starts with sodium, looking at the periodic table and moving across, that has 3 orbits. Yes, they also have an S, they also have a P, but then here they introduce what's called the D orbits, okay? And that's in the third energy level. If we continue with the fourth, which starts with potassium and goes across the periodic table, we have the S, also we got the P, we got the 4D, and we introduce the last orbit type that we have, and those are called the F, okay? So, again, the number in front represents the energy level, the coefficient 1, 2, 3, and 4. Everybody from energy level 1 to 7 has the S. Okay, so we denote that as 1S, 2S, 3S, 4S, etc. Starting with the second energy level going down, everybody has the P orbit, starting with 2P, 3P, 4P, etc. And ditto with energy level 3, where the D comes in, we get 3D, the 4D, the 5D, etc. From 4 down, we start the F, 4F, 5F, okay? All right, so this kind of diagram here, this diagram kind of shows you where these orbits are with respect to the energy level. So the very first energy level, we only have the S. Second energy level, we have the S and the P orbits. And the third, we got the S, P, and D orbits. And then finally, the fourth has S, P, D, and F orbits. The numbers, the levels, are the energy levels. The letters S, P, D, and F are designated as orbits, okay? Orbits. So orbits are, actually, I wish I could bring them in here, but basically what they are mathematical equations, humongous mathematical equations that represent, when we plot data of these equations, gives us a three-dimensional model that gives us an idea of where the electron is with respect to the energy level and the type orbit. And this gives you a high probability of finding an electron within that given area. Okay. Now, every orbital can hold a maximum. Let me restate that. One orbit can hold a maximum of 2 electrons. Okay. Remember that. Now, S, there's only one S. Okay. Orbit. And that can have at the maximum 2 electrons. The P's, there's 3 types of P's. Okay. There's in the 3-dimension X, Y, and Z, but there's 3 orbitals designated as the P. Each one can handle 2 electrons, so at the maximum, we can put for any P orbital are 6, okay? Now the D has 5 orbitals. And again, each one can handle at the maximum 2, so we can put a maximum of 10 electrons in any D orbit. And finally, the F has 7 orbits. Again, with 2 per orbit, we can put a maximum of 14. Now, let me bring you back to the periodic table, okay? Because this will hopefully make this a little bit, hopefully we can use a periodic table to, I can restate this, to help you with respect to where the electrons are. So I want you for a little bit to think, let me get the right tool here. If we look at this group here, okay, think of those as the S atoms. Now, how many columns do you see there? 2, okay, 2. Now, coming over here, in this group that I've highlighted, think of starting from boron to neon, think of those as the P elements. Now, count the number of columns across, starting from group 3 under boron, element number 5. You should count 6 columns. Over there, group 1 and group 2, there's 2 columns, okay? Now, let me change the color a little bit so we can show it. When you look at these elements right here, think of those as the D, as in David elements. Count the columns there. You will find 10 columns. Okay. And then finally, let me change the color again. These elements that come out here at the bottom, think of those as the F elements. And if you count the columns there, guess what? You're going to count 14. Okay. And so think of these as the S, the D, the P elements, and F elements. And when you do that, knowing that how many, what we just talked about, that in the S orbit, you can only put two electrons, starting with the first group in the first column, group 1A, that could be designated 1s1, 1s1, then go to the next level, 2s1, okay? But we'll get more on that in a second. So look, using the periodic table, that helps you determine when you get to those electrons, what orbit to put them in, okay? And so if I go across to boron number 5, it has a total of 5 electrons, okay? 2 of those electrons are in the innermost orbit, and then the second orbit, they're going to have 2 of them in the S and then 1 of them in the P, because it's starting up with the P in group 3, the P elements. Okay. So we'll have more to say about that in a second. All right, so this diagram here it should really be flipped upside down, because you start with level 1 at the bottom, work your way up. So within each box represents the orbit, and each box can handle 2 electrons. So I start off with level 1, which is hydrogen, helium. I only have the S orbit. I can put 2 electrons there. And so if I was just dealing with, let's say, hydrogen, this arrow would represent 1 electron, okay? Because hydrogen only has 1 electron. Its electron would be in the S orbit. And if I move across the periodic table and I got helium, it's got 2 electrons. So I put the second orbit in different direction, because they can't be going in the same direction, but I filled up the first level with 2 electrons. And if I wrap around to lithium, which has 3 electrons, well, 2 of them will go in the S, and guess what? The next one will go in the 2S, the next level up, okay? And I continued to move across to beryllium, its electrons, and that will fill this up, because beryllium has 4 electrons. And I shoot across to boron. Guess what? Boron has 5 electrons total, right? I got 2 in the S first level, then I fill up the S first, 2S, and then I go to P1. And as I continue across the periodic table, I first fill up each of the orbits. So this would be carbon. Carbon has 6 electrons, right? Total 6 electrons. 2 in the inside, first level, 2 in the second S level, and then 2P2, okay? And I keep going across to nitrogen. Nitrogen has 6 electrons, okay? Now I come up with oxygen and I start filling up the other orbit. It was empty. Then after oxygen is fluorine. I fill that up. And then finally, when I get across, all the way across with periodic table, guess what? I got neon. Neon has 10 electrons. Each arrow represents an electron. Do I not have 10 electrons there? Okay. And if I continue across and I go from neon to sodium, guess what? Where it's got to go? I can't put any more electrons on level 1 or 2 because they're full. So the obvious spot for sodium is in the 3rd level. And notice if you looked at the periodic table where sodium is, sodium begins in the 3rd period, okay? So that's how it works. You just progressively add the electrons across using the periodic table as a guide to help you. Now, when you saw the way we numbered it, 1S, 2S, 2P, and the coefficient represents the energy level. Now, to represent the electron, we use a superscript on the orbital. And so hydrogen, okay, hydrogen has 1 electron. Okay, so its designation, what we call the electron configuration, where the electron, how it exists would be in the 1st energy level, because that's where it's at, the very 1st orbit, which is S, and then it will be superscript 1, okay? That is the method to write the electron configuration of hydrogen. If it was helium, I replace that 1 with 2. 1 is 2. etc., etc. Okay. Superscript represents the number of electrons for that orbit, bearing in mind that the s orbit can handle a maximum of 2, the p orbit can handle a maximum of 6, the d can handle a maximum of 10, and the f can handle a maximum of 14. Okay. Now the s orbits, that model there kind of represents what happens when we take that mathematical equation and we plot data. You get this circular shape of the probability of the electron being in any of that particular area. Okay, the probability of the electron being found in that space. The p orbits, like I said, there's 3 of them. And their shape is, you call them dumbbell shapes. They're in the 3 axes. Okay. We have this one in the far left along the x-axis. And then we have the one in the middle along the z-axis, the z, and then along the y-axis. Now, all of those are together, you know, in the dumbbell shape. And keep it in mind that each one of these can handle 2. And hence, that's why for the p, we can handle a maximum of 6 electrons. Now, I can't show you the link for the D. We're not really going to talk about it. I'm going to see if the link doesn't work very well. I just got on that site and it wasn't working well. But when we get into the D and F, they get into some real crazy looking shapes. So we're going to bypass it for right now. Now, this particular diagram shows you how to fill, because we start at the lowest level, the first energy level, and we start as we move across the periodic table and we get the element that's bigger, has more electrons, we need to start filling the electrons up. But we fill them up with a specific order. Now this diagram here tells you the order. The order down here is you start off with 1s, 2s, 2p, 3p, 3p, and then you jump to the 4s, and then you jump to the 3d. The arrow here tells you, again, you start with 1s, 2s, that's the direction that you follow, okay? And now you can use this, which is fine, you can memorize that, or you can use the periodic table in the manner that I just described. Okay, because using the periodic table, you very quickly can write the electron configuration for any element on the periodic table. But be prepared to do at least the first 20. Okay, so let's go to the periodic table. So we can use that diagram. All right, I need to state something. Notice, let me cancel that for a second. Notice that we went here. If you follow the arrow, you go 1s. The arrow is going from top right to bottom left. So you go 1s and then 2s, the second energy. Then you go to 2p, 3s, 3p, 4s, and then you jump to 3d. Now this could be the confusing part, because where do we get to 3d? Well, let me explain. And to explain that, I need the periodic table. The 3d comes into play only when you start getting with number 21, when element number 21 comes into play, okay? Now notice that element number 21 is in the 4th period, count from top, 1, 2, 3, 4. And earlier I said, these guys in the middle, think of those as the D elements. Whoop, push the wrong thing here. Think of these as the D elements. Okay, there are 10 columns here, starting with 21, going across to 30, which is zinc. Okay, now they're in the 4th period. So the 4th energy level, right there, okay? And you would think, since we're going to number 21, that it would be 4D. Well, what happens is that the D orbits for number 21 don't actually begin on the 4th energy level. they are one energy in of where the element's at. And so really we start with 3D with number 21. Now you won't need 3D element, so it'll be 3D1, and if we go all the way across to zinc, it would be 3D10, superscript 10. Okay, so if you get to the D elements, bear in mind you got the D orbits. Keep track of what period it's in and just subtract 1. That's it. So that's where the 3D electrons come into play, but only when you reach number 21 and go across. Okay, so if, for example, let's do the periodic, the electronic configuration for boron. Okay, now we can very quickly, we can follow the diagram that you're given, or you can use the periodic table. First thing to notice is boron is in the second period. Okay, it's in the second period. So that's the first period right here. And obviously we got the third period right there. Let me type that in. Third. Okay, so the first period, second period. So boron's in the second period. That means that being in the second period, the first energy level is full. So we go 1s superscript 2, okay? 1s2, because boron has 5 electrons. The very first 2 electrons will occupy the innermost energy level, which is 1s2. Now we go across the periodic tables with number 3, and we go across number 3, number 4, that is the s electrons. Remember those? I said keep those 2 groups, think of those as the s electrons. Well, we already knowing that by looking at the periodic table, that's the second energy level, it's the s electrons, and 2 of those electrons are in the s orbit. And then as we shoot across the boron, I said think of those guys, starting with group number 3, as the p elements. So that's where the p orbits begin. And so we're still in the second energy level. So that's 2p superscript 1, right? Now count all the superscripts. 2 in the s first level, 2 in the second s level, and 1 in the p. Is there not 5 electrons? Yes, there is. Okay. Now, if we were going to do carbon, which is the one next to it, we just continue the trend. We put a 2 there. And if we're doing nitrogen, well, guess what? That's a 3. And see, I'm just using the product table. I go to oxygen, go to 4, right? Okay, how many electrons does oxygen have? Has 8. Do we not have 8 electrons as superscripts? Yes, we do. Fluorine, well, take that 5 off, make it a 4 off, make it a 5. Okay, and then finally, when we get to number 10, which is neon, we just fill up the p orbits and count the electrons that we have as superscripts. Guess what? There's 10, 6, 10 of them. 2 of them are in the 1s orbit, 2 of them are in the 2s orbit, and 6 of them are in the 2p orbit. Okay, and if we went around the horn for number 11, which is sodium, we recognize it's in the third period and it's in the s elements. So that would be 3s superscript 1. Okay, see how that's going along? And if I jump over to number 12, that's magnesium. That's an easy one. I just replaced that with the 2. And it continues, okay, all the way across. And if it went all the way across to argon, which is number 19, it will be 3, well, let me put a space here, 3 p superscript 6, okay? Count my math, make sure I got 18 electrons, and sure enough, okay, that would be the electron configuration for argon. So I'm using the periodic table, okay, find its position on the periodic table, find the period, remember which one are the S, which one are the D elements, which one are the P's, and you can very quickly write the electron configuration for whatever element that you're going to be working with, okay? But be familiar, at least right now, with the first 20, okay? And if we went around, guess where we're at? We stopped in argon, okay? All right, let's go around the horn, potassium, number 19. It's in the 4 period. It's an S element, right? So I've got to go S superscript 1 for let me open this up a little bit. For potassium, number 19, and number 20. Well, guess what? It's the neighbor. I'm just moving one more. It's 2. Okay. So there should be 20 electrons, and that's the electron configuration for up to calcium. Okay. So that's how I utilize the periodic table. Or alternatively, you obviously welcome to go back to that table and use the sequence they give you there. Okay. All right. Now, notice the trend when let me go back. I hope I still have it. Now, let me go back for a little bit to kind of introduce you to something. If you look at the Roman numerals on top, on the periodic table, now the horizontal, going horizontally, they're called periods, but going vertical, okay, up and down, they're called groups, and they're given a specific name, or I should say Roman numeral. Like this group here is group 1A, 2A, 3A, 4A, and all the way to 8A, okay? What that represents is what we call the valence electrons, okay? Now, we have the inner core electrons, and the valence electrons are the outermost shell, That's where all the action is with respect to chemistry, because if we're going to give up electrons or release them or gain them, it's going to happen in the outermost shell. The innermost shell is full, okay? And we can use the periodic table if you're asked a question, okay, sodium's number 11. How many electrons does it have? Well, it has a total of 11 electrons. Of those 11 electrons, one of them is in the outermost shell, okay? Magnesium, its neighbor, right next door, number 12, okay? It has 12 electrons, 12 protons. Of those 12 electrons, 10 of them are in the innermost shell, and 2 are in the outermost shell. I'm going all the way across to group 8A, okay? Those are the noble gases. With the exception of helium, He, number 2, it only has 2 electrons on the outermost shell, okay? Just 2. But everybody else, starting with number 10, neon, argon, krypton, and so forth, they all have 8 electrons. And that's where the magic number 8 comes into play. Because all chemical reactions, regardless of what's happening, their driving force is to have 8 electrons around this outermost shell, because that is the most stable state. And that's why group 8 are called noble gases, because the outermost shell is full and it takes too much energy to take an electron out. Or if I put an electron in, it's not going to go in that outermost shell. It's going to go to the next energy level, which is not energy favorable, okay? And therefore, they are noble and unreactive because they are obtaining the octet, as we call it, configuration, with the exception of helium, which is a duet configuration. So hydrogen and helium strive for the duet. Everybody else is striving for the octet. That is the driving force of trying to maintain 8 valence electrons in the outermost shell. Okay. Now, this is the configuration, the electron configuration for carbon. 1s2, 2s2, 2p2. Okay. Now, carbon has 6 electrons. Okay. And carbon is in group 4A. So just based on what I just told you, you know that carbon has 4 valence electrons. Those are the electrons on the outermost shell. Okay. And that is denoted by the electron configuration because the outermost shell is in the second energy level. Okay. So there's 2 in the s orbital and 2 in the p orbital. So there's 4 valence electrons, and it happens to be under group 4. Now, the other interesting aspect about the periodic table is if we look at carbon again, and let me highlight that so you know where I'm at, is right here, this whole group right there. Carbon's number 6, okay? Now, the reason they're put in that group is because every element underneath carbon, guess what? They have 4 valence electrons. Silicon, number 14, the one right below it, has 14 electrons total, but 4 of them are in the outermost shell, okay? If we look at group 1A, okay, all of them there have 1 valence electron, okay? Hydrogen only has 1 electron. It's the first element, so there's only 1 valence electron. That's why hydrogen is in that group. But lithium, the one right below it, has 3 total electrons, but 1 in the outermost shell. Sodium has 11 valence electrons, but 1 of them is in the outermost shell. Okay? And because they all share the same number of valence electrons, they all react very similar. So lithium and sodium, potassium and group 1 all have similar reactivity, okay? Carbon, silicon, very similar reactivity. And the same is true for group 7 on down here. Guess how many valence electrons that group has? Let's look at the Roman numeral, 7. So fluorine has 9 electrons total, but it has 7 on the outermost shell, specifically the 2s2 and the 2p5, okay? Chlorine, bromine, and iodine, all of them share the same property. They all have 7 valence electrons in the outermost shell, and therefore react very similar because they have the same number of valence electrons, okay? All right, let's go back to this. And so going back to carbon, we can see that the 4 valence electrons are 6 total, but 4 of them are in the outermost shell, the valence shell. Okay. Now we went through this already, where you start filling them up with the first level, and then move up. So level 2, you start with the S, fill those up, and then move to the P. Third level, you start with the S, move to the P, 1 orbit at a time until they're all full, and then move to the D, etc. for group 4. Okay. So if we look at the electron configuration for sodium, okay, we can see that it is 1s2, 2s2, 2p6, 3s1. We did that when I had the periodic table on. Okay. Sodium is in group 1. Okay? It has 1 valence electron, and guess where it's at? It's in the 1s orbit. Okay, you note it right here. That's a 1 valence electron. Oxygen is in group 6. Okay, so there's 6 valence electrons. Its total electron configuration is denoted as 1s2, 2s2, 2p6. Now, when you do the orbits, okay, sometimes students would take 1s1 and then add another 1s2. No, just keep them together, all the s. It'd be 1s1, and if you need to add another electron, then take that 2, make it a superscript. Take that 1, make it a superscript 2. So there should only be one denotation of denoted as 2s2 and 1 2p. Can go from 2p1, p2, p3, p4, p5, or p6. Okay. Oxygen has 6 valence electrons, and they occupy in the second energy level. So it has a total of 8 oxygens. Calcium is another one we just did. Calcium is in group 2. Guess what? It has 2 valence electrons that occupy in the 4th energy level, and 4s2. And then chlorine, being in group 7, has 7 valence electrons denoted by the superscript number here, 2 and 7. Okay. So work through the electron configurations and work them through, because this is going to explain why certain elements tend to lose electrons and certain elements tend to gain. The driving force is 8. Now, with that information, I can probably guess that you can probably figure out who, if I had to take an educated guess right now, based on what you know and what I've talked about, when I compare sodium and chloride, do you think sodium would want to gain electrons or lose electrons? Anybody want to take a guess?
Gain.
Okay, we got one gain. Keep it in mind the driving force is 8. Okay. Because if you look at the 3 energy level, 3s, you have 3s and the 3p. So in order you have a, let me look at the answer here. Gain for sodium, not quite. Okay. Because sodium wants to lose an electron. Remember this. Sodium has 11 electrons. The 1s level, 1s2 level is full. The next one is a 2s2 and a 2p6. That's full. So the one lonely electron is out further away. Okay, in the s orbit, it's further away, and there's only one of them. Now, in order to make that s orbit to be happy, it needs to gain at least 7 more electrons. Now, from an energy perspective, do you think it'd be easier to gain 7 electrons or just get rid of 1?
Get rid of 1.
Exactly. Much easier to lose that 1 electron all by itself, okay, than to pick up 7, because Mother Nature, you got to put energy into it. A lot of energy to gain 7. Yes, sodium can handle the 7, but it's going to take a lot of energy to put 7 in. So it's much easier to get rid of that. And if you get rid of that, guess what you have now as far as the electron configuration? You have 1s, 2, 2s2, and 2p. Excuse me, I can't find my 6. 2p6. And guess what? Sodium, by losing an electron, what do you think its net charge is now? Remember we talked about, I said the elements have +1, exactly. So it has a +1. Oh, that's not my plus. Here's my plus. Okay. By losing 1 electron, it started with 11 electrons, 11 negatives, 11 positives. It lost 1 electron. So now it has a net of +1. It becomes an ion. And that ladies and gentlemen, is what you ingest. You are ingesting the ion, which is nothing more than the element that lost one electron. And when it lost one electron, how many valence electrons does the sodium ion now have? Who wants to take a?
You're talking about the outer
Yeah.
balance shell. It will have a total of 8, which will make it an
Okay.
octet.
You got it. The sodium ion, now because it lost that one electron, and now that 3s1 is empty, it goes to the next layer in, which is the second. And guess what? It has 8 valence electrons, which is the driving force as to why it's much more stable, because it's searching for the octet, like the noble gases. Okay. Now let's take a look at chlorine. Okay. Based on what we just talked about now, what do you anticipate chlorine to do? Lose those 7 electrons or gain 1?
To gain 1.
Exactly. It's going to want to gain 1, because by gaining 1, you look at the P5, it has room for 1 more. Okay. And so when that happens, now its electron configuration is 1s2, okay, 2s2, 2p, oh, excuse me, wrong, 2p6, and then we got 3s2, and then 3p6. Okay, now chlorine has 17 electrons, the element. By picking up 1 electron, now has 18 electrons and 17 protons. What is its net charge now?
It'll be negative.
You got it. It'll be negative. And so now you have created.
And that's because it's gained electrons instead of losing, or right?
You got exactly. So now it has a negative charge, and we changed the name from chlorine to chloride. We'll explain more on that here in a bit. So what is for the chlorine, which is again an ion, okay? And being an ion, this is what you are ingesting when you put table salt in your French fries. The chloride ion, the sodium ion, okay? And so what is the new octet? How many valence electrons does the chloride ion now have? Anyone take a guess on that? Chlorine has 7, but now by gaining an electron, what is his new octet number?
It would be 8,
Count the
right?
electrons there in the electron configuration. The 3 level, 3s2, 3p6. What's 6 plus 2?
The 8.
8. So now the chloride ion, by gaining an electron, is now like a noble gas, the electron configuration, and which is a lot more stable state as compared to the element. So picking up an electron fulfills the octet. Okay,
So you're saying that anything that fills the octet will be a noble gas, period.
No, it will not be a noble gas. It will be like a noble gas with respect to the electrons. We have a name for that. We call that isoelectronic. Okay, that's important. Remember, in order for chlorine to become argon, what must happen? How can I make chlorine into argon? Anybody want to take a shot at that one? What must happen for chlorine to become argon, which is the next element next to it? Well, what would happen to, how can I make any element become another element? What is required? what defines an element? What subatomic particle?
The protons.
Exactly. So the chloride ion did not gain a proton. Just remember I said you can lose neutrons and electrons or gain them all day long. You still have that element. So all we did here is gain an electron. You still have the chlorine element. So now it's a chloride ion. Okay. And now the electron configuration is like argon, which is the gas in front of it. Because if you do the electron configuration for the gas in front of chlorine, which is argon, guess what you get? The same thing I just wrote here. So that it did not become argon, that's important, but its electrons became like argon, in which argon is a noble gas. Therefore, this chlorine, by gaining electron, goes more in the more stable state, okay? But the driving force of either losing or gaining electrons is fulfilling the octet, which brings me to a rule with respect to the elements. How do you know who gains and who loses? It's very simple. Put this in long-term memory. All metals, guess what? They lose electrons. They have the propensity to lose electrons, okay? All nonmetals want to gain electrons. And if you look at the nonmetals, based on what the periodic table I had before, guess what? They're very close to the noble gases. So it's easier for them to gain electrons, okay? To be like the noble gas in front of it with respect to the electrons. The metals, specifically groups 1 and 2, they lose electrons because by losing electrons, they're more isoelectronic or electron-like with the noble gas behind it. If you look at sodium metal, by losing that electron, it's a new electron configuration is 1s2, 2s2, 2p6. Guess what? Who has that electron configuration? Neon. Okay. So all the metals, by losing electrons, have the electron configuration of the noble gas behind it. All the nonmetals, by gaining electrons, have electron configuration of the noble gases in front of them. Okay. Let me bring that periodic table up. Notice the nonmetals over here. So nitrogen, oxygen, fluorine, they're very close to the noble gases. So from an energy perspective, it's easier for them to gain electrons. Hence, they become negative ions. The metals over in the far left, group 1 and 2, it's much easier for them to lose electrons and become electronically the same as the noble gas behind it. So sodium, by losing 1 electron, has the electron configuration of neon, okay? And that's important. It does not become neon, okay? It has the same electron numbers as neon.
And what did you say that term was called again? Because I'm pretty sure you're going to test it.
Isoelectronic. It will come up here in a bit.
Okay.
So, yeah, iso meaning the same, electronic meaning the electrons. They have the same number of electrons, okay?
Okay, got it.
All right. So earlier I showed you, manually the periodic table, and I said, hey, think about the S elements and so forth. Well, this diagram shows you again, okay? The S orbits, you can put 2 maximum electrons. So we got group 1A, the S1, S2 is a move across. The P start in the yellow, okay? The D's are within the center, or the B, we call them BL. We call them B right now. They have a specific name later on. And then the F electrons, F elements down at the bottom, okay? Notice that they correspond to the number of, if you count the columns for the D's, there's 10. In the D's, we can put a maximum of 10 electrons. The F, we have a maximum of 14 electrons. While there should be 14 columns right there for the F elements. The P in yellow, we can put a maximum of 6 electrons. And so you can see there's 10 columns as you go across the periodic table, starting with group 3A and so forth. So the periodic table is a good guideline to help you with the electron configuration, or alternatively, you can memorize that number they gave you and use that. Whatever works best for you. I prefer just glancing the periodic table because for me it's just quicker. Okay. Now, here's the electron configuration. Now, if you look at the Ds, they do bounce around. If I look at 3D, the light green color, okay. For Chem 130, you simply go 3D, 1, 2, all the way across to number 10. In reality, they do fluctuate because that's where you get 1, 2, 3, and it hops to 5, goes to 6, and hops around. For us, we're just going to go across the board, D1 to D10. The F, the same thing from F1 to F14, okay? But you can see that the P's consist P1, P2, P3, P4, P6, so forth. So this here, using the periodic table on top or using the chart that is given to you at the bottom, whichever works for you with respect to writing the electron configuration of an element. So, be familiar how to write it for the first 20. You'll be okay. Okay, so we talk about noble gases in group 8. That's the last column on the far right of the periodic table. They are very stable and happy, whatever happy means, but I prefer the word inert and unreactive, okay? And they are because all the orbits are full. They got that magic 8, okay? With the exception of helium, because it only has 2 electrons. So, but still, it's 1s2. That orbit is full. So the common thread that they all have, with the exception of helium, is the octet, or the 8 valence electrons, okay, that make them stable. I repeat, the valence electrons are those electrons on the outermost shell. The ones inside, we call those the core electrons. They're the ones that really, they're full, they're not going to do anything, okay? So all the action, all the chemistry occurs on the valence electrons. Okay. So we have phosphorus here as an example, and there's the electron configuration for phosphorus. 1s2, 2s2, 2p6. Phosphorus is in the 3rd energy level. And as we go across the periodic table, we fill up the 3s2, and then we fill up 3p3. Okay. Phosphorus is in group 5, A, from a numeral 5A. So it has 5 valence electrons, which are denoted here by the purple color. Okay. Those are the 5 valence electrons. Now, if you had to take an educated deduction here, would you anticipate phosphorus to gain or lose electrons? What do you think?
Gain?
Exactly. First of all, it's a non-metal. Okay, like I said earlier, put this in long-term memory. Metals lose electrons. Non-metals gain electrons. Okay? So that right there should have told you right away, phosphorus, where is it on the periodic table? Oh, it's a non-metal. It will gain electrons. Okay, so that's correct. Now, how many electrons do you think it would gain?
3.
Exactly, 3. By gaining 3 electrons, guess what? The 3s2, the valence shell now becomes 3s2, 3p6, okay? Which means the octet, the magic octet has been fulfilled. Now, what happens to the charge of phosphorus when it gains 3 electrons?
It becomes negative, right?
Yeah, how much negative? It does become negative, but there's a magnitude here. If it gained 3 electrons, what do you think its new charge would be now? Okay, well, let's look at it.
I would just assume -3, wouldn't it?
Exactly, be -3. Phosphorus is number 15, okay? 15 protons, 15 electrons, net 0. It's a nonmetal, so when it becomes an ion by gaining 3 electrons because the octet is fulfilled, now it has 15 protons and guess what? 18 electrons. What is the net? -3, okay? And by becoming -3, now it is an ion. And now we change its name to phosphide. Okay, right above phosphorus. Right above phosphorus is nitrogen. Okay, how many valence? Let me answer this. Is 2? Are you talking, Aziz? You talking about 2? Or no, Ali? 2. No, it would be 3 because remember it's got 5 valence electrons. The driving force is to get to 8. So to get to 8.
Time is up,
needs-
Dr. Fred.
Yes. Somebody had a question. Oh, yeah. Thank you. All right. Yeah, I went over the amount. Okay, I thought you were talking about electrons. You're telling me about the time. You are 100% correct. Let me stop it here, and we will continue next Tuesday. Let me see where we at. Let me make sure. Okay. So we will continue next Tuesday. On page 31, I will upload this as soon as it gets converted. And let me stop. So any other questions?